In this tutorial, we will look at how to solve for the concentration of solution using molarity units. In Chem 51, we will use solution molarity often. It is important that you have a good understanding of solution molarity and be able to solve a variety of molarity problems. This tutorial, and the following one on mixed solutions and dilutions, review the basic concepts of molarity and dilution and provide sample problems like you will encounter in Chem 51. Molarity is defined as the moles of solute divided by the liters of solution. This represents a ratio of measurable quantities. Molarity is what we call an intensive property, which means that its value does not depend on the size of the sample. If I have 1 liter of a 1 molar solution and I pour out 10 milliliters, the solution is still 1 molar overall. For comparison, recall that density is also an intensive property. Again, it's a ratio of two quantities, mass to volume in that case. When a solute dissolves in a solution, the solute particles spread out evenly throughout the solution. For example, if you dissolve 8 moles of solute in 1 liter of solution, the molarity will be 8 molar, because we take the molarity equation, put the moles of solute on top, and divide by the liters of solution. If you take that 8 molar solution and pour out 1/4 of the solution, or 250 milliliters, there would be 2 moles of solute in that amount, but the molarity is still 8 molar, because 2 moles of solute in 0.25 liters is equal to 8 molar. Volumetric flasks are usually used for making solutions of known molarity because they are designed to contain a certain volume of solution. Analytical balances are also used to weigh out the required mass of solute to achieve the desired number of moles of solute. The weighed solute is added to the volumetric flask and dissolved in a small amount of the solvent. More solvent is added with swirling until the solution level is at the base of the neck of the flask. The final drops of solvent are added with a dropper until the bottom of the meniscus is at the calibration line. Then the flask is capped and inverted to mix thoroughly. Note that volumetric flasks have only one calibration mark. It's not possible to estimate between markings in this case. When using a volumetric flask, you must get the meniscus on the line. Otherwise, you have to remake the solution. Let's work through an example of solution molarity calculations. What is the molarity of potassium chloride in a solution made by dissolving 25 grams of potassium chloride in a 100 milliliter volumetric flask? Molarity is defined as the moles of solute per liter of solution. The solute in this problem is potassium chloride. To convert 25 grams of potassium chloride to moles of potassium chloride, we use the molar mass of potassium chloride. 25 grams of potassium chloride divided by 74.55 grams of potassium chloride per mole gives 0.335 moles of potassium chloride. The volume of the solution is the same as the volume of the volumetric flask. However, we need to have it in liters rather than milliliters, so we do the conversion between milliliters and liters to get 0.1000 liters of solution. Substituting these values into the molarity equation gives us our final answer of 3.35 molar KCl. Now try this problem on your own. What is the molarity of a solution made by dissolving 35 grams of sodium hydroxide in a total solution volume of 150 milliliters? Click to pause the video as you solve the problem. The answer will be shown on the next slide. This presentation dealt with simple molarity calculations. In Chem 51, we will often make solutions by mixing several solutions together. Continue with the next activity on mixed solutions and dilutions to see how this is done.